Hello everyone, welcome to YouTube channel Energy Exergy Theory Applications. I am Tatiana Morosuk and I am author of this channel. Today we are with the lectures on engineering thermodynamics. All lectures have a very dynamic style of presentation. Definitely some of you would like to learn more. We will be happy to answer your questions and provide with extended information. Please find our contact email in the description of this video. The first lecture on engineering thermodynamics is dedicated to basic definitions. We will start with approaches used for thermodynamics, and after that we will revise the basic definitions. What means system, what means thermodynamic state, and what means thermodynamic properties. There are two approaches for thermodynamics. One approach is called macroscopic approach, another approach is called microscopic approach. In general, we should use one approach or another approach. Combination of these two approaches, no one never will use because it is not meaningful. Macroscopic approach very often is also known as classical thermodynamics. We'll discuss only the gross, or better to say, overall behavior of the system. What it means? It means that we never will discuss on the structure of matter. We will never discuss about molecular, atomic, or even subatomic level. In opposite, in microscopic approach, which is also called statistical thermodynamics, the structure of matter plays very important role. And for example, if we need to discuss some processes involved lasers, plasmas, or high-speed gas flow, chemical kinetics, it is chemical thermodynamics, or very low temperature application, cryophysics. For such applications, definitely should be used microscopic approach, because structure of materials are very important, and without knowing of structure of material, we cannot discuss thermodynamic processes. Any energy conversion system is a set of components. Which components are usually formed any sort of energy conversion systems? It is compressors, pumps, turbines, sometimes call it expanders, heat exchangers. Different kind of heat exchangers can be not only heat exchangers but also heat mass exchangers, mixers, separators, chemical reactors, and any other devices. And very often chemical reactors, it is general term, but particular cases of chemical reactors, for example, combustion chamber, it is also can be considered as a chemical reactor. These components are connected between each other within the energy conversion system by circulation of working fluids. It can be one working fluid or different working fluids, and at present working fluid, it is the most commonly used term instead of working substances. Many years ago, working substances was a more popular term than working fluid. And for engineering thermodynamics, and our idea is to revise engineering thermodynamics, only macroscopic approach is used. Microscopic approach we will not even discuss, we will not even consider. So I just would like to pay attention that only macroscopic approach will be discussed. Many energy conversion systems interact with surroundings through work and through thermal interactions. Energy conversion system, it is a very general term. What means energy conversion system? It can be thermal system. Many years ago, thermal system was very popular term. Now it's not commonly used. It can be power plant, which is more clear for us, but also can be refrigeration machine, can be heat pump, and can be any sort of energy conversion system that also belongs to the category of cogeneration system, multi-generation system, hybrid system. So any system where we have energy conversion processes can be generalized by general term energy conversion systems. And now we can see that two words definitely should be defined, two terms. It is term system, and this is term surrounding. And our next discussion will be focused on these two terms. Many energy conversion systems interact with surroundings through work and through thermal interactions. Energy conversion system, it is a very general term. What means energy conversion system? It can be thermal system. Many years ago, thermal system was very popular term. Now it's not commonly used. It can be power plant, which is more clear for us, but also can be refrigeration machine, can be heat pump, and can be any sort of energy conversion system that also belongs to the category of cogeneration system, multi-generation system, hybrid system. So any system where we have energy conversion processes can be generalized by general term energy conversion systems. And now we can see that two words definitely should be defined, two terms. It is term system, and this is term sorting. And our next discussion will be focused on these two terms. In thermodynamics, particularly using macroscopic approach, the term system is used very widely, and we need to identify subject of analysis through introduction the term system. So using very simple definition, system, it is whatever we would like to study. We need to subtract system from everything around, say that this we would like to study, and everything which is not system, call it surroundings. So it means that we need to introduce only in our imagination some system boundary, and everything which is included in this boundary will be our subject for analysis. Everything which is out of this boundary is called surroundings. In general, for us, it's very easy to understand thermodynamic system and surrounding. But with a modern kind of analysis, for example, if we would like to apply economic analysis or even more complex life cycle assessment for environmental analysis, this definition of system and surroundings really play a much more important role than for thermodynamics. That's why we need clearly defined what is system, what is surroundings, and give several examples. Here on this figure, we can see, so this is a figure, this is photo of power plant. And for example, we would like to study only power plant itself. Therefore, power plant is separated from everything around using system boundary. And such an example, it is so-called fixed boundary. Definitely power plant is not movable, it is on the ground. That's why we will discuss about fixed system, fixed boundary, and all analysis will be done under these conditions. Another example, system can be also not only energy conversion system. Under system, we also can discuss the behavior of working fluid. So working fluid itself also can be system. Then to discuss the processes with working fluid, boundary conditions can be movable. For example, we have some volume of the gas and we would like to discuss the compression of the gas. Then for us, it's completely irrelevant where compression process is taking place. We will discuss only gas that is compressed. Therefore, system boundary should be also moved together with the gas. And such a system boundary will be called movable. Let us proceed with the definition. One more time, we have system and everything which is not included to this system, call it surroundings. But the word surroundings is not very often used, and sometimes it's difficult to understand what means surroundings. I mean technical meaning and our everyday life. Therefore, surroundings sometimes is replaced with more clear term, natural environment. So when we discuss environmental impact, we have environmental pollutants and any emissions, we always will refer to natural environment. So surroundings and natural environment, it is absolute the same. It is not even alternative words, it is the same meaning. So in this figure, you can see that system, it's given in red color. So for example, power plant, and everything which is not included, it is surroundings or natural environment. In modern thermodynamics, we need another definition, and this definition is called thermodynamic environment. Thermodynamic environment, it is something which is not realistic. Thermodynamic environment does not exist in real life. And I always say to my students, we cannot touch, we cannot see thermodynamic environment. It is something artificially introduced to thermodynamics to finally to make engineering life easier. So it means that with definition of thermodynamic environment, we can significantly simplify some theoretical discussions and after that proceed with some calculations. This is very important, and I will remind you with the term thermodynamic environment when we already discussed the second law of thermodynamics. But here we should really distinguish between natural environment and thermodynamic environment. It can be the case that properties of natural environment and thermodynamic environment will be absolutely the same or can be very close to each other. But nevertheless, we always should define thermodynamic environment. So if this concept will be used for any sort of analysis, this should be clearly defined. Let us continue with the system. Again, some definitions. We have three three kinds of thermodynamic systems. We have open system, we have closed system, and we have isolated system. What it means? Every time a system here is given in a gray color, so something which we would like to study. We will not now discuss what is inside of that. We introduce a system boundary. This is Dutch red line, and we can, and of course we have surroundings. And we say that for open system, energy and matter allow to cross the boundary of the system. So energy and matter can circulate between surrounding and system or between two systems. For closed system, matter cannot escape from the, so cannot cross the boundary conditions, cannot escape from the system, and only energy can be transferred to system from system. And for the isolated system, neither matter nor energy can cross the boundary of the system. So these three kinds of system, open, closed, and isolated, we will discuss further, but for engineering thermodynamic, isolated system are not included in the field of engineering thermodynamic. Therefore, we always will discuss only for open systems and closed systems. So, closed system and open system. For students, usually it is quite difficult to understand what means matter cannot cross the boundary of the system, and for open system, matter can cross the boundary of the system. Let us proceed with a little bit more engineering discussions, how to describe closed system and open system. Closed system, we can say that matter will circulate between system components, but will not go out from the system. So it will be continuous circulation between the components. Yeah, and energy can be transferred to the system and from the system. This is closed system. If for some reason we would like to evaluate only one component from the system, we need to introduce new boundary conditions, and then each particular component from the system can be discussed as open system, because energy can be crossed, energy flow can cross the system boundary, but these two blue arrow, it is exactly the circulation of working fluid to component and from component. So I will repeat, if we would like to discuss the energy conversion system when working fluid circulate only between the components, it is closed system. But if we would like to discuss, to evaluate each particular components, which is very important if we would like to simulate system, we always will simulate component by component, then each component will be already particular case of open system, because working fluid will flow of working fluid will cross the boundary conditions. Let us continue with a review of definitions. What is its state? State of the system, it is conditions. under each state, for example, I can say that system at state 1 or is at state 2, it means that behind there are some conditions that will be characterized as state. And state always should be given at instant period of time and described by properties. So now we have another term, properties. What means properties? It is any quantitative characteristic of the system. So means property cannot be better or worse. We need to give number for each property that we would like to discuss. And property always depends on the state of the system and independent of the history of the system. So for us, does not matter how long it took to achieve this property. Important that this we will achieve the state that is required. All properties are divided into two kinds or two categories. We have intensive properties and we have extensive properties. Intensive properties independent of size of the system. So for us, does not matter how big will be system, properties always will be the same. And intensive properties, usually it is temperature and pressure, because does not matter how big is system, temperature will be the same, and also pressure, independent of size of the system. If it is given pressure, pressure will be the same. Extensive properties depends on the size of the system. So it means that there are properties, numerical value of these properties depends on how big is system. Now we need to discuss what means size of the system. It is volume, it is mass, or it is number of molecules. So the size of the system can be described by these three characteristics. Therefore, extensive properties, I repeat, depends on the size of the system. And sometimes we have extensive properties, of course, but we would like to exclude the size of the system. We would like to calculate these properties per kilogram, per cubic meter, specific volume, or we would like to calculate on molar base, means per mole. Then these extensive properties divided by a unit of mass, volume, or molar base, call it specific properties. We all know there is specific enthalpy, specific entropy, specific internal energy, and so on. So it means that these extensive properties we divided by unit of mass, unit of volume, or on molar base, and we will discuss extensive properties on specific level. Another term, equilibrium. Equilibrium means conditions of balance. Now, which equilibriums exist in thermodynamics, and particularly in engineering thermodynamics? The easiest to discuss, of course, it is thermal equilibrium. It means that it is equality of temperature. Another equilibrium, it is mechanical equilibrium, it is equality of pressure. Both thermal equilibrium and mechanical equilibrium, of course, we can directly measure. We can use thermometer in order to measure temperature, or manometer in order to measure pressure, and we can have definition of equilibrium, to make our decision is system in equilibrium or not, through direct measure. But also there is one equilibrium which is called chemical equilibrium. Chemical equilibrium means equality of chemical potentials. Chemical potentials we cannot measure directly. It is so-called indirect measurements, means we can only calculate this value. And for the people who are not very well familiar with chemical thermodynamics, I can give very brief information that chemical potential, it is equilibrium, so chemical equilibrium, it is equilibrium in chemical potential, which is a partial molar Gibbs energy. So it means that to define chemical equilibrium, we need to go to the second law of thermodynamics already and discuss Gibbs energy and even partial molar part of Gibbs energy. What means two states are identical? When can we say that two states of the system identical? It is possible if and only if, as you can see from this slide, if all properties of system at these two states are identical. So it means that we have list of the properties, and these properties should be absolutely the same for one state and for another state. If we have at least one property is different and all other properties are the same, it means that it is already not identical. And if this property will change from one value to another value, we can say that system is undergo a process. So now process, it is change in properties, at least in one properties. And when system will go through the many processes and finally return to the same state, so initial state and system will go through many processes and return to the same state, we can say that it is a cycle. And in engineering thermodynamics, we have only two simple cycles. We have direct cycle and we have inverse cycle. So the definition of inverse and direct cycle only associated with the clock. So in direct cycle will follow the clock, and inverse cycle will go to opposite direction. In engineering thermodynamics, we have theoretical cycles, we have real cycles, reversible cycles. So already for engineering application, we can use hybrid cycles, combined cycles, whatever it's possible. Any combinations, of course, we will discuss within different lectures, but now we are with basic definitions of thermodynamics, of engineering thermodynamics, and we will deal only with two basic cycles, direct cycle and inverse cycle. Your next lecture will be dedicated to the first law of thermodynamics and concept of energy. And at the end of our first lecture, I ask you to give a like to this video, to subscribe the channel, and share the link of this video with your colleagues. Thank you.